So hello, here we are going to look at the momentum of a system of particles in a particular frame, and that frame is the center of mass frame. This frame has same velocity and acceleration as the center of mass of the system of particles. So we can have any number of particles moving around with their own velocities, with their own positions, their own accelerations. So this is a very general scenario. In this case, if you want to write the momentum in the CM frame, it is quite intuitive that it will be the summation of their individual momentum. So we write down the momentum of each individual particle, which is its mass, mi, times its velocity in the CM frame, which is its velocity in some lab frame. So Vi is the velocity of the particle in some particular laboratory frame, and these Vi's are known, suppose. So, but we want to write the velocity in the CM frame, so we subtract VCM from it. So this whole thing, this whole summation is the momentum in the CM frame of the entire system of the particles. So if we distribute this bracket, if we open this bracket, we find these two terms, and these two terms turn out to be exactly equal because of the definition of VCM. So VCM is defined as the total momentum of the system in a laboratory frame, and VCM of course is also measured in that laboratory frame. So it is the total momentum of the system divided by the total mass of the system. So if you plug this formula in here in the second term, you will find that these two terms reduce to the same thing, and the momentum relative to the CM of the entire system, the total momentum of the system, is 0. So this is a very interesting conclusion, and you can also think of it like that this is a way to define the CM frame. The CM frame is a particular frame looking from which the total momentum of the system reduces to 0. So let's move on to the kinetic energy. The kinetic energy in the CM frame can also be reduced to a particular formula by some mathematical calculation. So we start with this. This is the definition of the kinetic energy in the CM frame, that if you have velocities of the particles in a lab frame, you subtract the velocity of the CM, and you get the individual velocities in the CM frame. So you plug it here and you get this summation. So if I expand it, the square of the modulus of this vector is just that vector dotted with itself. So if we open these brackets, we get this first term, which is mi square. We get the second term. So in the second term, VCM square comes out of the summation because it does not depend on the particles. It's a common thing for all the particles. VCM is a constant, if you want to say. It's not a constant, but it's a constant in the sense of if we are moving from one particle to the next, VCM is not changing there. VCM is common for all the particles. So if I do the summation of over each particle, I'm multiplying the mass of that particle with the same VCM every time, VCM square every time, and therefore VCM square comes out, and we get this summation of the total mass, which becomes the total mass. And then the third term is because of is the cross term, because of the dot product between Vi and VCM, and again VCM will come out. So similar to the second term, VCM comes out, and then it becomes a summation over just MIVI, which again MIVI is again can be written in terms of the VCM as we see in this bracket. So it turns out that these two terms are exactly the same with different factors in front. So the factor here is half and the factor here is -1, but otherwise these two terms are exactly the same, because once you put this here, you get VCM dot VCM, which is VCM square once again. So you get this. So the first term stays as it is, and the second term is generated from these two terms. So we get this. So this is sort of our final result, except that I want to take this negative second term over to the other side and rewrite the relation as this. So if I look at this relationship, the left hand side is just the kinetic energy of the system from the lab frame, right? The second term is some kind of kinetic energy of the center of mass, and the third term is the kinetic energy of the particles from the CM frame. So let us look at it properly over here. I'll repeat myself. The first term that we get here is kinetic energy in the lab frame. It's very simple, right? So it's just, if I'm looking from the lab frame, which usually in problems we call it the ground frame, and that is the frame in which we know all the velocities, the VIs. So this is the kinetic energy from that original frame. And this third term is the kinetic energy in the CM frame, which we started out calculating. This is what we started out with, this is what we wanted to calculate. But we sort of inverted, we took that one term to the other side. We took this first term to the right side of the relationship and completely changed the relationship. But now it is in a more useful form, in a form which is more illuminating. And this form can be summarized as below, that the total kinetic energy of the system of particles in a lab frame is the sum of two parts. Just like this relationship is completely analogous to a simple relationship in terms of the velocities or the accelerations, that the velocity of a particle in a lab frame is equal to the vector sum of its velocity in a particular frame and the velocity of that frame itself. So it's very similar here. The kinetic energy in the lab frame is equal to the kinetic energy in the CM frame and the kinetic energy of the CM itself. And what do we mean by the kinetic energy of the CM itself? I have put this term in quotes over here, that kinetic energy of the CM, because the CM is not a particle, it's not a real particle, it's not a real body as such. But if you consider the entire mass of all the particles concentrated at the CM, and obviously the CM has a particular velocity, and you calculate this product, half m, this is the total mass. So there should have been brackets over here, but yeah, and because VCM comes out of the summation, it's common. So this is kind of the kinetic energy of the CM, which I've put in quotes because the CM is not a particle actually, but it's like if all the mass is concentrated at the CM, then if you take this product of half times total mass of the system times VCM square, you get some kind of kinetic energy of the CM. So we can also understand this relationship, this equation in another sense, that if you're looking at a system of particles from the lab frame and they're moving around, their energy can be categorized into two parts. They have some kind of total kinetic energy, they're moving around, and that total kinetic energy is obviously what we have written on the left hand side. It's as simple as it gets. This is the total kinetic energy, but it can be categorized into two parts. Like the system has an internal motion and it has an external sense, in a sense, an external motion. What I mean by that is, if you look at the average, so I'm kind of using this language, but don't get too carried away with this language. I'm just trying to make a little sense of this relationship so that you remember it better. This is just a way to sort of remember how this relation comes out. So the total kinetic energy is the sum of two parts. One part is the average, is kind of the average motion of all the particles, which is characterized by the motion of the CM, because the CM is sort of like an average. It kind of to the outside observer, to the observer who does not know the minute details of the motion of the particles, is only seeing the velocities, is only seeing the velocity of the CM, suppose. So from macroscopic sense, so if you are very far away from the system of particles, all you will see is what they're doing on an average. That it's a cloud of dust particles, for example. So you will see that, okay, or it's a cloud of water droplets. So you see the average, but you don't see the change in shape. You don't observe that, or you're not able to observe the microscopic stuff that is happening inside. So what you're observing from the outside is the velocity of the CM, and this is that kinetic energy. The kinetic energy of the CM is what you see from outside, from far away. And the other part is the inner motion, is when you enter the center of mass frame, right? When you enter the center of mass frame, you see the velocities of the particles relative to the CM. So that is kind of like its internal matter, right? So this is how we can make sense of this relationship. In general, this first term on the left hand side is clearly known. It's because we know the velocities in the lab frame. The second term is also known because we know the velocity of the CM in the lab frame. This third part is more complicated, because if you have a very large number of particles, it will be a complicated matter to exactly calculate this term. In some situations, it's very easy to calculate. We will look at this in the next video on a case-by-case basis. But this is the term which is the internal sort of energy of the system, and it depends how we calculate it. It depends on what the system is like. So thank you for watching.